Now that we have an idea of what SN2 and SN1 is and the basics of SN2, let's talk about some more details that goes with SN2 stereochemistry. Okay, so remember again, I'll keep telling you that the nucleophile attacks from the back in SN2. Back attack only by nucleophile. Okay, the nucleophile will attack from the back. So if someone pushes you from the back, you're gonna respond in an opposite way. So like the saying goes, action and reactions are equal, but opposite in direction. So you will expect if there is a push from behind, then the groups that are on the left will be switched to the right, and that's a sign of inversion. So here is your nucleophile. All right, the reaction is concerted for SN2, so it happens at once. The nucleophile attacks the electrophile. So we use the lone pair to attack the carbon center. See, you are doing a back attack, right? And then this falls off by SN2 mechanism. So the bromine would be a leaving group. This is what we call a transition state, where this bond wants to form. The bond is forming here, and the bond to bromine is breaking because bromine is a leaving group. Now, I want you to see that the methyl, ethyl, and hydrogen, these, and these are on your left. When the reaction is done, they're going to be on the right because there was a push by the nucleophile from the left side. Now, that's visual representation of inversion, okay? Inversion. So we can assign chirality. Okay, let's assign chirality. Let's assign chirality and see. We are starting with this molecule. Of course, you have CH3 there. You have CH2 here. And the hydrogen. So the hydrogen will get priority 4. It's the babiest attached to the chiral center. And then using Kern-Ingold rules, bromine will have highest atomic number compared to the groups directly attached to the central carbon. So priority 1. The ethyl will be priority 2 because that carbon is bonded to 2 hydrogens more substituted. 2 hydrogens and a carbon. This carbon is bonded to 3 hydrogens. So obviously the one bonded to a carbon and 2 hydrogens will win over the one bonded to 3 hydrogens. So this method will be priority 3. So we focus on number 1, 2, and 3. Right now we are going clockwise. Then before you really say that the chirality of this carbon is R, you check and look at the smallest group. It's towards us. The true assignment should be given when the smallest group is away. See, there's a shaded wedge, so it's towards us. It needs to be away. So whenever it's towards us, the chirality is R. What would be the chirality if the smallest group was away? It would have been an S, and that's why we call this S. Now, as far as the name goes, as far as the UPAC name goes, this is carbon 1, 2, 3, 4. So it's 2-bromobutane. 2-bromobutane. But now we are including one more name, one more part of the name, the chirality S. So after the OH attacks, you get this product. Let's determine and prove that the chirality is R. Okay. Now, the smallest group has to be away. Right now, it's on the plane. It's not even towards, so we cannot just switch like we switch here from R to S. So I've proved to you that the chirality is S. You need to try and prove that the chirality here is R. It should be an R. So after the reaction, okay, the S compound is turned to an R compound. That's inversion. All right. Racemization happens with SN1. Inversion happens only with SN2, but with SN1, you're gonna have racemization. So racemization just means you have a mixture of a race, like black and white human races. But now here the races we are talking about is R and S. So racemization of chiral atoms will occur in SN1. The reason being SN1 always goes through formation of a carbocation, and the carbocation has a C plus center, which is sp2 hybridized, and the molecular shape of the C plus in the carbocation will be trigonal planar. Now, I want to emphasize planar, which means flat, either flat on the table or flat on the plane on your monitor. So suppose you have a tertiary carbon, because we said tertiary carbon will not do SN2. Suppose you have a tertiary carbon. For example, let's say you have 3 metals and a bromine. This carbon here is tertiary because it's bonded to 3 other carbons. Okay? So the nucleophile cannot come to attack. Okay? The nucleophile cannot come to attack because the backside is hindered. That won't happen like we did here. The backside is hindered. This carbon right here is secondary, so it's possible because SN2 goes with methyl halide, primary, secondary, and then we say the tertiary will not do SN2. But for SN1, it prefers the opposite, tertiary, secondary, primary, and in fact, these two will never do SN1. So this is tertiary, so it's good for SN1, bad for SN2. So SN2 will not happen, the nucleophile will not attack in the first step. Instead, the leaving group has to leave. That's what we are showing here. The leaving group leaves. When it leaves, you make a carbocation. The carbocation has a C+. Like I said, the C+ is sp2 hybridized. There are 3 electron domains, 3 bonds, so it's sp2 and trigonal planar. The leaving group left. Now, if you have the nucleophile, only then will the nucleophile come to attack. And it's going to attack either from the right or from the left. So which means you might end up with equal amount of R and S. So especially if R1 is not the same as R2 and R2 is not the same as R3. If R1, R2, R3 are not the same, then you're going to end up with chiral centers, equal mixture of R and S. So like 50% chance to make R isomer, 50% chance to make S isomer. So that's what I'm describing here. So you get 2 products depending on the approach of the nucleophile. Okay, so if the nucleophile attacks from the right, then this is what you get. If it attacks from the left, this is what you get. If this carbon ends up being chiral and this ends up being chiral with 4 different groups, then you'll have equal amount of R and S or S and R depending on what R groups are. Okay. The labeling here, prime and prime prime, just means R plane, R prime prime, and R prime are different. That's what makes these carbon centers stereogenic centers or chiral centers, and therefore you have equal amount of R and S. Because the carbocation is flat, you have equal chance attacking from the left or right or from bottom or top. Okay? So I need to give an example here. Let's see if I can create a table. Okay, so let's describe what we've said. So let's start with SN2. We said SN2 leads to inversion of configuration. So let's give an example of that case. So you're gonna need a nucleophile. So let's say we have OH minus, right? And then we are attacking chiral carbon. Let's assume we have such a carbon. So if you're attacking from behind, okay, if you're attacking from behind, then you will expect that these groups will be flashed back, so they will face like this, keeping their stereochemistries. but this time the OH will be here. And of course, there's always a second bond for SN2, it's concerted, so Cl minus. So let's qualify and see if we really have inversion. So hydrogen is priority 4, chlorine priority 1, ethyl group will be priority 2. You can follow the Canning-Gold rules. I'm not gonna go into details, but I know I'm doing it right. So we are going 1, 2, 3. Okay, so this is an R isomer. So the stereocenter here is R. And in fact, the name will be R 2-chloro, because this is carbon 1, 2, 3, 4. You give the chloride the substituent the least number possible, 1, 2, 3, 4, 2-chlorobutane. Now you do your attack, Cl fell off, you get this product with the groups that are on the left now flash to the right, keeping their types of wedges. So oxygen priority 1, hydrogen 4, ethyl priority 2, methyl priority 3. So this time we are going 1, 2, 3, and we are going S. The smallest group is away here. It's away here. No need to switch our RNSs. We keep what we get. So the answer here will be S. The name here will be S, and then 2-butanol, because you have 4 carbons. 1, 2, 3, 4. Okay. All right. So you see the R isomer is the R stereocenter is changed to S stereocenter, and that's inversion. Now for SN1, let's assume that I give you a nucleophile like H2O, because SN1 works with weak nucleophiles anyway, and then we are attacking same molecule. So let's say this is our molecule. Probably we have what group? Let's say we have a metal here, and then up here isopropyl, and then let's say we have a chloride. Now you see there's a hydrogen here. The metal has 3 hydrogens, and here the ethyl has 2 hydrogens. Of course, this is the stereogenic center, that's the chiral carbon, because there are 4 different groups. You have the isopropyl group, the ethyl, the methyl, and the chloro. So 4 different groups. Now, the carbon bearing the leaving group is bonded to 3 other carbons, this, and that. So this is a tertiary alkyl halide. I don't expect SN2 to happen because the nucleophile will be hindered by the carbon groups on the back side to the leaving group. So we'll have to think SN1, which goes first by formation of a carbocation. That's the rate determining step. Okay, the Cl fell off. Now the Cl can decide to attack from the left. No, not the Cl, sorry. The nucleophile can decide to attack from the left. So let me do that. So if H2O, the nucleophile, comes now to attack from the left, then these groups will be pushed to the right. So you will end up with probably this. Okay. And now, remember, organic molecules don't like to be charged. So one more step, you're going to use a water molecule to do what we call proton transfer. See, that's why I told you SN1 has so many transition states and a longer mechanism compared to SN2. So your ethyl is there, and now you're going to have your OH, and of course the water will be now H3O plus after it takes out the extra hydrogen. So I want you to focus on this product. Okay, but you have the other option where the water can decide to attack from the left. Okay, in which case you'll have the ethyl group to the left, the methyl group to the left, and the water to the left. Okay, and then again, the organic molecules don't like to have charges on them, so we use an extra molecule of water that will act as a base to take out the extra hydrogen. So in that case, you will have OH to the left, and then you'll have ethyl, and then you'll have your methyl there. So again, focus on this molecule. Remember, we are showing formation of two molecules because there are two ways you can approach the carbocation intermediate. Okay, so the OH is here, OH is there, and then you have the methyl and the ethyl. So you have two possible products, this and this. Let's assign chirality. Oxygen, priority 1. Of course, the smallest of all these carbon-containing compounds will be the methyl, priority 4. And then isopropyl only has one hydrogen on that carbon. The ethyl has two hydrogens. So obviously the isopropyl is more substituted. If you want, you can follow the Canning-Ingold rules as described in chapter 5. And then you'll find that this one will win because this carbon is bonded to two carbons. This carbon is bonded only to one carbon. So this gets number 2, and then this gets number 3. The oxygen gets number 1 because oxygen has high atomic number compared to the carbon. Okay. So now here our numbers are going 1, 2, 3. We are going towards the right, and that's R. The smallest group, number 4, is away, so we keep the R. If this is R, then this has to be S. 1, 2, 3, and 4. Yes, it's an S. You have 1, 2, and 3. So you have an S. So this compound here will be 50% equal chance to be formed. This will be 50% equal chance to be formed. Those two products are called racemic mixtures. Racemic mixtures because they are equally formed, because the carbocation can be equally attacked from either side. I think now that's clear. Here I've explained how you get racemization of products, equal rates of R and S. Here I've explained how you get inverted products, R to S. Okay, so since the mechanism affects the stereochemistry of the product, we want to control the mechanism. There are a number of ways we can control the mechanism. If you either want to go SN1 or SN2, there are things you can tweak in your reaction conditions to make sure you only have the SN1, or you mostly have SN1 versus SN2, or you only have SN2, or you mostly have SN2 versus SN1, because both of them are substitutions. So if there is a way to favor one over the other, that's what us organic chemists like doing, because if you don't do that, there's gonna be a lot of mixtures in your products after the reaction, which gives you a very hard time to separate and give you a miserable life. So what are the factors that are used or changed to favor SN1 or over SN2? Okay, number 1 is the nature of the substrate. Okay, so SN1 versus SN2. The nature of the substrate can dictate whether you're going SN1 or SN2. Remember, SN1 goes through formation of a carbocation, and the more substituted the carbocation, the more stable it is. We talked about that in an earlier chapter. I told you inductive effect and hyperconjugation stabilizes the carbocation. So the more the alkyl groups, the better. That's why SN1 prefers to go with tertiary over secondary over primary, while SN2 does not like sterics on the backside because the nucleophile cannot do the back attack. So SN2 will want the backside to be open, and in that case, SN2 will prefer, first of all, the methyl X before the primary, before the secondary, and the tertiary will almost never do SN2. Okay, so SN2 requires backside attack, so sterics will hinder it. So again, in summary, if you are to consider SN1, okay, if you are to consider SN1, SN1 will prefer tertiary substrates. Remember, tertiary substrates will contain carbon-containing groups, 3 of them, bonded to a carbon bearing the leaving group. Okay, that's tertiary. So like this carbon bearing the leaving group, this leaving group could be something like Cl, Br, or iodine. So if the 3 carbons are bonded to a carbon bearing the leaving group, then once the Cl falls off, you're gonna get a tertiary carbocation, and tertiary carbocations are more stable than primaries. That's why tertiary substrates are preferred for SN1. Okay, because the carbon containing groups will donate electrons through bond to better neutralize the plus charge. So for the secondary, you will just have 2 carbon containing groups bonded to the carbon bearing the leaving group, and this will give you the secondary carbocation of this nature once this leaving group falls off. Okay, once the leaving group falls off, to give you the carbocation, because that's what happens in SN1, is formation of carbocation. Carbon containing group bonded to carbon bearing the leaving group gives you a primary, because this carbon is bonded only onto one other carbon. And then of course the least reactive or non-reactive, of course, will be the methyl X, but it's going to be the reverse for SN2. SN2 doesn't like sterics on the back side of the leaving group, so the methyl X will be more reactive than the primary more reactive than secondary more reactive than tertiary. In fact, tertiary never does SN2, because SN2 requires back attack of the nucleophile. The back side is crowded, the nucleophile cannot approach this partially positive carbon to attack it. Okay, and you have the examples here. This is primary. Let's see, no, this is not primary. This is methyl bromide. Okay, while this one is a primary alkyl halide, because this carbon right here is bonded to one other carbon. This is a secondary alkyl halide. The carbon bearing the leaving group is bonded to 2 others. This is tertiary. The carbon bearing the leaving group is bonded to 3 other carbons. So for SN1, it's gonna prefer this one, because once the leaving group falls off, guess what you form? You form a tertiary carbocation, which is more way stable than the rest. The more the alkyl groups surrounding the C+, the more stabilized the plus charge will be, the more stable the carbocation. So the tertiary alkyl halide will react 100 million times than a methyl bromide. Okay. Now for SN2, the backside of this guy is hindered. So if the nucleophile like OH- tries to attack from the back, it's just gonna be thrown back by the big alkyl groups. So this one almost no reaction. In fact, cannot be measured. But look at the primary. Here, the carbon, the partial positive carbon, is very, very exposed to be attacked from the backside. So this reacts 220,000 times than whenever you have a secondary alkyl halide. And of course, the rate for the primary alkyl halide is just 1350. So sterics control SN2. Okay, like we said here, sterics will control SN2. The more accessible the electrophile is, the more reactive the electrophile will be, governed by sterics. If there's branching, that's gonna create a lot of problem, because again, if you look at these guys, all of these are primaries, right? You see the carbon bearing the leaving group is bonded directly to one other carbon. So this is primary. This 2 is primary, is bonded to one other carbon. This 2 is primary. This 2 is primary. They are all primaries, but the rates are different, because if you introduce a larger group onto the primary carbon, then you're causing sterics. Now, if you're causing sterics, what happens to SN2? So SN2 hindered. All right. So if you branch off this group, you are creating more sterics or crowding, and the SN2 will be hindered, judged by these rates of reactions. Next effect we'll discuss is solvent effects.